Okay, so I guess we'll get started. I'll just start by introducing myself so you know who I am. So I'm Dr. Gardner. Hopefully you're in the right place. Hopefully I'm in the right place. This is ECE2700. So this is going to be your introduction to digital circuits. So just so I kind of get a feel for the class, who here has taken other electrical engineering courses? Okay, was it, how many of you were in 1270? Okay, so most of you are doing, so for those other ones, 1270 isn't a prereq. So for those, the bulk of the class, you're going to be having essentially some review here just because we need to establish a common language when we go into this class. So that's a lot of what this class will be. But for me, so I graduated with my PhD about a year ago coming out of the University of Utah. I have also spent about 4 or 5 years working in industry. I worked for L3, which is one of the larger employers of engineers around here. I've also worked for Berkeley National Lab in California. And I have worked for a neurotech startup here in Salt Lake City that developed implantable medical devices. So brain implants, really. And so I kind of have seen both the kind of academic side and the industrial side. So if you end up with questions on either one of those, I can answer them. So supposedly I am primarily an analog designer, analog integrated circuits for implanted medical devices. But what you'll find out is if you're an analog engineer, a huge part of industry is moving towards digital. This class, 2700, and the next in the series, which is 3610, tend to be really important classes for your field, almost no matter where you end up doing work. The other benefit, this class is kind of fun. It's kind of interesting. It's going to start out really kind of technical and we're going to get through, but we have to establish a common language because you haven't really done anything like digital circuits. You've never seen anything quite like this, unless you were lucky and your high school had something maybe. So how many of you know what an Arduino is? Okay, so a couple of you. Another term, the general term for Arduino is a microcontroller. It's like a simple processor, a dumb processor, right? So it's not going to be able to run Windows for you or anything, but what it can do is it'll take usually something like C, and you can program it and easily access digital inputs and outputs. Digital meaning it's 1 or 0, true or false, on or off. You'll hear all of those terms for digital inputs and outputs, right? Where you've seen them, almost certainly, most people have seen on YouTube where those really fancy light shows from like Christmas, right? Where all the lights are kind of flashing along to the music or something. Those are hobbyists that have taken a microcontroller and programmed it to play music and change lights based on what the music is doing. Other things people use them. So my younger brother, he built a temperature and humidity controller system because he breeds snakes. Many of you will end up using something like an Arduino for your senior projects. What this class does is actually going to build up your knowledge so that you can reach the point where you will know how to build a microcontroller. In fact, your final project is a 3-part project, really. We call it project 1, 2, and 3, but it's really building up one, where you will build, using code, a microcontroller, and it will actually be able to execute commands. Now, that sounds like a lot, and it's actually a pretty hard project, but most students finish it. It is achievable. Now, we are designing circuits, and we will start by using our hands on what we call breadboards. If you've taken 1270, you've certainly used breadboards. If not, they're not too hard, and we'll go through those in the lab for next week, I believe. So eventually, though, we're going to switch over to code. We're going to program it. How many of you are familiar with programming? So again, most of you. Now this is what's kind of funny. So what we're using is VHDL. So VHDL is what we call an HDL. It's a hardware description language. A hardware description language describes hardware. It's not like Python or C or any of these other ones, because those are software languages, and they actually have more flexibility than an HDL. Now myself, you're going to see issues if you're really good at programming, learning HDLs, because they're different. And you'll think, oh, this should work in software, and it won't work in hardware. They're different, and we'll go over what that means, and we'll learn how to program if you don't, and we'll change how you think about programming if you already know how, because they are different. Yeah. So ultimately, later on with HDLs, you can build massive systems. So the circuits in your phone that allow you to call someone on the other side of the world are built in a hardware description language, in an HDL. Most of the time, it's actually Verilog. So there's two HDLs, Verilog and VHDL. There's others, but those are your big ones. Verilog is used primarily by the civilian sector, and VHDL is used primarily by military, government. And a lot of Eastern European countries actually still use it, as well as Southeast Asia. The benefit is, if you know VHDL, it's really easy to learn Verilog. I learned Verilog, and supposedly Verilog to VHDL is harder, and it was not hard. And I'm not a super strong programmer from a software sense. But HDLs are a little bit different, and they're interesting, and you're really designing circuits. And we'll get into kind of what that means and what circuits we're talking about, and we'll kind of introduce some of that today a little bit. Okay, so the syllabus. I've handed this out. Does anyone not have one? So I'm not going to read every word to you. I expect you to read every word. A lot of it, especially the tail end, is just kind of stuff about the current state of things, right? We have to be a little bit different and flexible in current schools. But I'll start off. As I said, I'm Dr. Gardner. I have office hours listed here. One thing I've noticed with younger students, and I don't mean that age-wise, I just mean new to college, is that you tend to be scared of using office hours. Office hours aren't there for me to judge you about what you're doing wrong. It's just free tutoring. Well, free, I mean, you're paying tuition, and part of my salary is for me to sit in my office and play video games while nobody shows up to office hours. But you guys can use them, and no one's ever there, so it's pretty available. You can also schedule time with me via Zoom during those office hours, and I'm a little bit flexible on outside of those office hours for Zoom meetings if you need help. Be aware they do tend to get used up as we get closer and closer to the exam, and it gets harder and harder to help, really, because there's more students that I'm dealing with. So if you start getting lost or confused, use office hours early. Okay, but they're listed here on this, and the syllabus is posted online, so if you lose this, it's not the end of the world. The text, this guy, you'll see some versions online say with CD-ROM. You don't need the CD-ROM. And in fact, if you want to use the second edition, you're okay, but you're just going to have to work with someone else to get, like, just ask a fellow student for the homework problems, because I'm going to assign some homework out of the book. And so you don't want me to say, like, oh, do problem 2.16, and then you pull second edition 2.16 and get it wrong. Homework is mostly about you guys learning the material. If you do it, all of the problems, and you get them all horribly wrong, you get 50%. If you do it, and you get most of it, well, all of them wrong, but it was almost right, you get 75% of the homework. Right? The grade on the homework isn't really about getting the right answers. And likewise, don't really care if you reach out, like on Chegg or Course Hero and that kind of thing, for help on the homework. However, on an exam, the exams are going to be take home, kind of. They're what I would say do from anywhere. I'm going to post them online, and you guys are going to have an hour and a half to take the exam, and then just upload it back to Canvas. It will be open notes, open book, open internet, with the one caveat that you cannot create new internet content for it. So no posting questions to Chegg or Course Hero or Stack Overflow when you're taking the exams. Homeworks are fine, exams not so much, right? Treat the homeworks as learning the material. Don't just copy the answers, because then you're going to get to the exam and then you're going to post to the internet because you're desperate. And then I'm going to answer the question on the internet wrong, and then I'm going to fail you in the course. You laugh, I did this last semester, I'm not joking. So don't cheat on the exams. They're not hard, I promise. This class is kind of fun and it's not that hard as long as you put the work in. If you put it off, you're gonna get lost and confused, and it's really hard to catch up if you fall behind. Okay, exams and homework, you will need to know how to turn something into a PDF. Your choice of how to get there is yours. But say if you want to print out the exam, and you can come into the class for the exam. I will be here if you don't want to take it somewhere else. So, and I will hand out printed out copies, and then you can turn those in. If you're taking it remotely, you will need to either take a picture of it or scan it and upload it to Canvas. For homework, same thing, you need to upload it for Canvas. Now on one of these pages, the second page, I have this whole list of homework guidelines. One of the important ones is submitted as a single upright PDF. I don't like it when they come in upside down or sideways because that increases my grading time by a lot. So to make sure they're PDFs and they're upright. We want your name on it. I want your answer circled. I don't want column separations ever. I want all vertically separated problems in the homeworks. And then when we get to code, I will show you, actually it might be on the syllabus online, of what your kind of code submissions are supposed to look like. I don't want you to just copy and paste your code into Word or something because then the formatting gets all screwed up. What I describe it as, let's see, what did I say? Online, I didn't update this one for some reason, I missed it. What I want for code is to follow best practice tabbing requirements. So if you programmed in Python, you'll do it instinctively because Python requires the tabs to be correct. But we'll talk again, show you code of what properly tabbed code looks like when we get there, which will be not too long. This course, I'm actually using a different book than I've taught this class before on, so there's going to be some changes in here. If I lose you guys, something get confused, or it feels like it's going too fast, don't be afraid to speak up. Like, I don't necessarily know where you guys are going to be at because I'm kind of trying some new things out. Don't be afraid of asking questions. You're going to probably see me screw up on the board today. I'm not going to judge you if you make a mistake because some of this is really hard to wrap your head around. And even if you're out of practice, if you just for a little while, you can kind of lose track of how to do it. So if you're confused, it's understandable. This is different thinking than you've gone through before. There is a topic outline, kind of what we're going to be talking about. Most of those words may not mean much to you yet. We'll get there. The third page, I'll leave mostly to you. And last page. Okay, yeah, there's this lab notebook guidelines on the last page. That's the general rules. I'm going to be kind of lenient on those. The labs. So this class you can take either in person or remotely. For the lectures, I am recording it overhead camera. The resolution leaves a little bit to be desired, but it seems to be fine. And I had students get A's last semester using the recordings only. The lab is a little bit harder to do remotely, but still possible. If you plan on doing it remotely, you're going to need to reach out and email me because you're going to need some parts that you're not going to have lying around your home. And so I can start giving you some of those components that you would need. And now, right, and this whole reason is COVID kind of sucks. So I caught COVID almost 9 months ago, and it about killed me. So if you're worried about COVID, especially if you have someone at home at risk, I really understand that you don't want to be here because you feel it's risky. I will do everything I can to make sure you succeed remotely. That being said, it does tend to be a little bit harder remotely than in person because this was designed as an in-person class. Okay, let's see, I think that's all I get. Oh, the syllabus, one last thing. You'll notice the grading is at the bottom of the first page, and it actually spills over onto the last one. There's this little section called professionalism. Basically, all that is, and I've never had to use this, is the saying if you're a mean person, I can deduct your grade, which is just don't insult people, don't bully people, don't take your mask off in class. Just simple things like that. I've never had to use it. I hope I don't ever have to. People are generally good people. Okay. I'm going to be posting a chart that looks something like this. Again, this is just to help me if somebody catches COVID, so we don't have to isolate anyone that doesn't need to be. This is different. This is for my different classroom. I haven't made the chart for this one yet. I'm going to post an assignment. This will be the easiest points you get all semester. Actually, second easiest points you get all semester. Where you're just going to fill in the number of where you sit. And I'm just going to assume you're going to sit there all semester. And that way, if they reach out to me and said, oh, somebody sitting in number 6 they'd see Joe got COVID. You need to send people that sat around him into quarantine, right? They needed to let know. And then I'll just say, all right, it was this student, this student, this student. This seating chart, let me do that. Number wise, it's just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So just take note of where you're sitting. If there is someone that ends up watching this that is remote, I think you can sit in 1 or 3 if you end up watching on video to fill that in. If you plan on staying remote the whole time, just write remote and it's fine. The easiest assignments, and I'll remind, the easiest points you get all semester is at the end of the semester, you guys have the option of filling out review, right, of me and the class in general. Of course, feedback. You'll get extra credit if you fill that out and just show proof that you filled it out. I don't need the answers, I just need it, you filled it out. But I will remind you when that gets closer. Okay, so I've kind of alluded to what this class is about, right? We're starting out with digital circuits, and then we're gonna learn how to make those using code. And we're gonna use something called the Vado, which is kind of the design environment for VHDL. It is a free tool. It's a little bit tricky to install on your own, so I will provide a walkthrough of how to install it. It is installed in both that lab and the lab that we'll be using down the hallway. So you don't need it on your laptop if you're coming into the lab. If you're doing the lab remotely, you do need to be able to install it either on a laptop or a PC at home, something. It's kind of a big program. I think you need like 30 gig or something to install it. It's actually a pretty good design environment. I like it. Okay. I posted a homework assignment already. I actually think I need to add a little bit to it. It's only like 10 problems, and it may get postponed a little bit depending how far I get in this class today. We'll see. Okay, so let's start with some basic terminology so that we're all on the same page. Now, some of you, this is going to be boring because you've taken 1270. So electricity has, well, 3 major components that we need to concern ourselves with. The first one, I think we've all heard, volts, right? V for volts. This is like your 9-volt battery. The next, I stands for current. I know, confusing, but its unit is amps. So volts, so we'll just do this, the unit, volts, amps. And the other one that we're going to be interested in this class, there are others, is resistance, R. Who knows the unit of resistance? Ohms, OHMS, or ohms. And now you're going to hear it, you're going to hear me say stuff like, say 40 kiloohms. Little k, kilo, means 1,000. So that's 40,000 ohms. Similarly, you might see me say something like 30 millivolts. 30 millivolts is equal to 0.30 volts. This means divide by 1,000. The next one for that, micro. mu, like a little squiggly u, right? That is just divided by 1,000 twice. Okay, now this all comes together into what we would call Ohm's law, meaning that the voltage, current, and resistance are related through that equation, V equals IR. So we can think of this like water. Current being the easiest one to visualize, right? Current is, in the water analogy, the flow of water. Resistance, you can imagine as the size of the pipe. The smaller the pipe gets, the higher the resistance is, the harder it is to flow. Resistance, right? It makes it harder to flow. So if you imagine a big pipe that suddenly drops down to a small pipe, right? What's going to happen to the water? It's going to back up behind that. That backlog of water is the volts. So the current flowing into the resistance creates a backlog of water called volts. Now this matters to us. We're not going to do a lot with this, but we, as I talked about, are going to be using digital I/O, inputs and outputs. Now we can imagine that no device has the ability to generate infinite current. From that assumption, right, it's safe to assume that there is some limit. And generally a good number for a lot of this is like 20 milliamps. So we're going to cover some basic devices. Again, the 1270, I know you know all of this, but gotta make sure everyone starts in the same spot. So if I wanted to say have a light that tells me visually if a digital I/O is on or off, right? True, false, 1 or 0. Then I want to create a circuit that prevents it from blowing up either my source or the LED. So say I have an LED that limit is 20 milliamps. That's pretty common. It's a reasonable number. So let's say I have a 5-volt source. I write the source like so, 5 volts. What this means is from negative to positive, I'm raising 5 volts. This is what we draw as a resistor, R. And then we come down through an LED. This is how we draw LEDs. In an LED, this bar means current doesn't go that way. Current only flows through that way. Now, we're going to be doing some stuff with this in lab. So let's say I have a limit of 20 milliamps. I have 5 volts. And I want to ask the question, or rather I want to design such that I never blow my LED up because that's obnoxious, right? So how do I ensure that I limit the current to 20 milliamps? Yes. So the easiest way, right, is to rewrite the equation first with I on one side, because that's what R on one side, because that's what I'm solving for, right? I need to know what resistance should I use based on this voltage and the known current limit. So R is equal to V by I, right? Okay, so now I can just say, well, that's 5 volts, that's 20 milliamps, that's my R, right? Except there's a little bit of a trick to this. So you're going to notice with LEDs, they're going to have a voltage associated with them that they're going to try and maintain no matter what. This voltage is usually somewhere between 0.7 and 1.3 volts. So let's say 0.7. Then what we actually have to do for V is it's just the voltage drop over the resistor. So the voltage is going to drop over this resistor 5 minus 0.7. I do that and I have the resistor size that I need to protect my LED. Now, if I were to increase the size of the resistor, the amount of resistance, does that increase or decrease the current? Decreases the current. So all that's saying is that my resistor R has to be greater than or equal to that value. That's the extent, really, of Ohm's law that we have to worry about voltage solving, but you are going to have to do that, more or less, in order to both protect the circuit and the LEDs. A clue that you've done poorly on your resistor calculation is either that it's too bright or too dim. If it's shining and you can barely look at it, your resistor is too small. The more current, the brighter it gets. If it's super dim, your resistor is too big. Okay. So you noticed me draw, actually I just realized a couple of other symbols that I didn't explicitly address. That symbol means ground. So voltage is not absolute. Voltage is relative. So if you took two 9-volt batteries, right? They're both 9 volts, but they're not necessarily, the positive terminals are not necessarily the same voltage. What they are is they're 9 volts relative to the negative terminal of that 9-volt battery. Right, does that make sense? The difference is between absolute and relative. Okay, so the ground is what we usually use as a reference. It can mean literally earth ground. So like in the case of the electrical sockets, they have an earth ground, and that's established by driving a metal pole into the earth. And that's their earth ground reference. Doesn't necessarily mean that, and like your phone, right, it's like the metal chassis that they're using as ground. But you need to, that's all that symbol means. If I use other symbols that you don't know, if you haven't taken 1270, reach out, ask me questions, raise your hand. Most students kind of take 1270 in this parallel, and that's kind of what the assumption is, but it's not required. So if you aren't doing that, slow me down. Okay, the circuit that I drew before that had a resistor, an LED, and ground. This is called a series circuit. I was able to calculate the current through the LED by calculating the current through the resistor because they must be equal, right? I can't, if water is flowing in, water has to flow out. It can't just disappear. The same holds true for electricity. If the 20 milliamps is flowing through the resistor, 20 milliamps must be flowing through the LED. It can't disappear, it can't increase. You can have parallel circuits. Now those two, if they're like this, that means parallel, right? If those resistors are the same, they'll both have the same amount of current. But we don't do a lot with parallel circuits, but if I'm talking parallel, you're going to hear me talk about serial and parallel in multiple contexts. Because you have parallel circuits, but you can also have parallel data. So serial data is just, it's a string. It's like a backcountry road, right? One lane, you go that way, and 2 cars can't go at the same time. Parallel data is like the highway, you have like 4 lanes, 4 cars go at the same time, right? Serial and parallel, that concept is going to come up a lot. The next idea, when I'm talking about electricity, I'm going to be talking about ground, power, and signals. Those are the 3 essentially types of electricity that we're going to concern ourselves with. Now, power, you're also going to hear me say as power, rails, what's the other one? You might also hear the terms VCC, VDD. We'll get into what those are referencing, but the DDCC, they're referencing the rails, the power. I don't ever use them. You can also see VEE as one of the power rails, and VE. Does anyone remember the other one associated with EE? No, it's all right. No one uses that. Okay. So that's power. I've talked about ground. Now signals. Signals are the other one. This is what contains data. In our world, in the real world, right, everything is what we call analog. So can anyone tell me an example of an analog signal?
Original or radio broadcast. Haven't they changed the radio to digital, but they use
They have both. Yes, but yeah. So radio is actually starts out as an analog signal. Another analog signal is my voice. Analog, right? It's a series of waves that is propagating from me to you, carrying data, information. Digital signals. Digital, right? 1, 0, on, off, true, false. What is an example of a digital signal? Something that is either on or off. Nothing in between. Light switches, right? Digital. Light switch, on, off. Now you have dimmer lights, right? But your switch, if it's like this in this room, is just on or off. There's no in between. There's no kind of on, right? When we draw a switch in a circuit, it looks something like this usually. I may or may not include that arrow when I'm drawing on the board because I'm lazy. All this is the switch is open or closed. Open means it's not connected. No current flows, nothing goes through. So if I have this circuit, right? A voltage is applied here, but if this circuit is open, that voltage doesn't pass through, and therefore this light cannot turn on. If the circuit is closed, that means that switch is closed, and the current can flow through. Now, other times you'll see various ways. This needs a signal to tell it when it's on or off. So you might see something like, I'll just modify this one. I think this is how the book does it. Where that's a switch controlled by X, where X is what we call a variable, right? So X tells it open or closed, on or off. X is the variable that determines by it. So variables, we know variables, right? We've taken algebra or calculus or wherever we're at. It says something like f of x is equal to x squared, right? And we can solve that. We're going to run into the same type of thing in digital logic, except for, fortunately for all of you, we won't have to do any calculus. We're just going to go into what we call Boolean algebra. Boolean is a counterpart to decimal, right? So Boolean is zeros and ones. It's not 1, 2, 3, 4, 5, 6, 7, 8, 9, and then repeat, right? It is 0, 1. Well, let's count. Let's show some binary, right? So this is counting in binary. Right? 0, 1, 2, 3 in binary. Where the ones place can only be 0 or 1. So that, right, scales up, but not by factors of 10. It's up by factors of 2. We're going to be drawing binary a whole lot. And there's actually other ways to represent numbers that we will get to down the line. But for now, just be aware that when I'm talking binary, when I'm talking digital or Boolean, I'm considering counting in binary. This is an idea that we need to be comfortable with, and we're going to kind of build upon later. Okay, so we could redraw this, call this function f. Now this is f of x, where the output depends upon the input variable x, right? And in that simple equation, if x is 1, f is 1. We have another idea where we can say invert it. When I'm talking Boolean, I don't necessarily always say invert, right? So invert is essentially take the opposite. If it's a 1, make it a 0. Now there's no concept of inverting in decimal, right? What does it mean to invert the number 10? Who knows? Inverting a decimal binary is flip the bit, right? Each one of these is a bit. Therefore, this is a 2-bit number. This is our sequence of 3-bit numbers. Remember that binary is 0 indexed, meaning we start counting at 0. So this is 0, 1, 2, 3, 4, etc., right? 0 indexed. I will try my best to make sure I 0 index everything in this class. So if I have a sequence of numbers, we call that n, and n goes from whatever, I will try and start with n0, right? So n5 is not the 5th number in a series, it's the 6th number in the series. Right, so I'm 0 indexed. Keep that in mind. Okay, we good if I erase this? All right, so now we're going to start talking about logic, digital logic, which is the core of this class. Now, logic you've heard of, like, right, you have the Star Trek version of like philosophical logic, just think reasonably. This logic is hard and fast. There's no arguing about it, there's no opinions about it. It's just how the rules exist. Now, I'm going to teach you a tool that you would never really use to develop anything, but it helps you visualize what logic is talking about. We're going to have these operators. So you're going to hear me use the term logical operators. Examples of logical operators are, making sure I stay in the screen, and, or, not. Those are some examples. These operations are saying that if are two things both true in the case of and, or are either of these things true. So let's go ahead, and you've probably seen something like this before. We call them Venn diagrams, X and Y. All right, so let's describe this. What is a term using a logical operator that I could describe as this region, the shared region? Yes, so this region is X and Y, right? If I say X or Y, I mean the whole thing, right? So if I say X or Y, I can color it in. And what we're evaluating is what part of this is true. Does this region have both X and Y? Or does this region have X or Y in it? Let's build this up a little bit. Okay. What is this region?
X and Y and Z.
Exactly, X and Y and Z. Okay. Someone else. What's this region?
Z and Y.
Exactly. Now we can actually describe this one probably a little bit differently, but we'll get into that in a second, right? Because we can start using the not variable. So we can start saying not X. Not X would be all of this Y and all of this Z and this region here because there's no X. But X is everywhere else, right? Not X. Okay, let's get a little bit more complicated and start doing something useful. What if I want to say, I want this region and I want that region? How do I describe those two regions in one expression, right? I'm essentially saying F is equal to, and you'll notice I'm not going to do the of X because to do that properly, I would have to do F of X, Y, Z is equal to, right? And that's going to get tedious for all of us. So I'll drop that pretty consistently. Okay. So what I want to do then is actually connect these through OR operators. So OR is saying this region or that region, right? So I can say F is equal to, well, this one is Z, not X, and Z, not Y, right? So what I say, and the way I write this, is I'm going to put out the variables X, Y, and Z. And I like Z, but I don't like X or Y in that term. So I use a bar over it. Not X, not Y, Z. I can explicitly draw the multiplier symbol. In Boolean algebra, multiplication is and. Or is a plus sign. So those two regions, I'm saying F is true if I have not X, not Y, and Z, or X and Y.
You have to add not Z to that.
Oh, absolutely. Because, good catch, if I had not included that not Z, I would also have that region here. Right? Because if the Z is not in there, we'll get more into it later. It means we don't care. I don't care what Z is if it's not in that expression. So regardless of what Z is, if I had X and Y, it would be true. By adding the not Z, I exclude that region. So now we can use this as a tool to evaluate if two things are equal. So what that's going to say is something like, where's a good example? Okay, so if we want to test that X and Y sorry, just making sure I write this down correctly, otherwise I'm going to get really confused. Okay. So if we assert that that statement is true, we can use a Venn diagram to evaluate if it's true. And we're going to do this. There's going to be one of these on the homework. They're fortunately not that hard, right? It's a tool to evaluate if things are equal. We can just draw out the Venn diagram and then start filling in the bubbles. So where is X and Y? Well, we kind of did that one, right? It's X and Y, including that middle region. Not X and Z. So that's the whole Z region without the X. Y and Z. Well, Y and Z. Right? That region. It's already filled in. So it's unnecessary. I don't have to have that term. I don't have that term. Everyone see that? That term quickly becomes obviously irrelevant. Does anyone not follow that? You need to prove it. This example is somewhere on page 36 of the textbook. I believe that you can go back and kind of look at their walkthrough of that example of these Venn diagrams. They're not that complicated. What I want you to get out of these Venn diagrams is the visual understanding of what these logical operators are telling you. Okay. So now I'm going to switch gears a little bit on you and start, well, not too much. We're going to move on from the operators as words and start using operators. That's the vocabulary word for all of these. If I use an operator, I'll try and always write it as all caps so that it's clear what it is. But we're building circuits, right? So what I want to do is I want to be able to draw circuits that do these operations. Let's start with AND. This is an AND gate. It does the logical operation of AND. What does the logical operation of AND mean? Well, let's bring back some stuff, right? The counting and binary combined with a new idea of what we call a truth table. Okay, so let's call the inputs A and B and the output C, A, B, C. And then here, I'm just going to count in binary. Now, when you're only doing 4, it's easy. If you start doing more than 4 rows, right? Sorry. Let me explicitly point this out. If I have 2 variables, I'm going to have 2 to the 2 rows. Broader, I can just say I will have 2 to the n rows, where n is the number of bits in my number. So if I had added a third variable d, I would have 2 to the 3 or 8 rows. Now you can just count up in binary, which is not hard, right, once you start figuring it out. Or you can do a trick, and I will just do this for an example purposes, where every time you go to the next column, you just double the number of sequential zeros and ones. What I mean by that? Well, the first one is 0, 1, 0, 1, 0, 1, 0, 1. The second one is 0, 0, 1, 1, 0, 0, 1, 1. The next one, 4, 0, 0, 0, 0, 1, 1, 1, 1. Makes it easy to start filling out these truth tables, of which you will be making a bunch of them. All right. So let's simplify this down to only the rows I actually need to evaluate this AND gate. I should have left it up, but that's all right. So AND. This is saying the output C will be true or 1 when the AND condition is met. What does AND condition mean? What does the AND operator do? Well, when I have both A and B, it's true. Which row of this meets that condition?
Very last one.
The very last one. None of the others do. That's my truth table for my AND gate. Take just a moment to appreciate my fine artistic skills and go ahead and write me out the truth table, write in your notes, the truth table for the OR gate. Okay, so all the OR gate is saying that I want it to be true if A or B is true. Well, neither of them is true, so it's a 0. The rest of these have at least one 1 in them, so the rest are 1. Hopefully everyone got that. The next gate not. This one has the simplest truth table, well, the second simplest. Right, because I only have one bit, I only have one input, so I only have 2 rows. 2 to the 1 is 2. If the input is 0, the output is 1. Now the reason that this NOT gate looks like it does is it's derived from the buffer symbol. The buffer symbol just states the output equals the input. 0, 1. So you'll notice the difference between the NOT gate, or the buffer, and the NOT gate is this little bubble here. Bubbles mean NOT. So if I go back to my AND gate, and I add a bubble at the output, this then becomes a NAND gate. Not AND, NAND. Okay, what does the NAND gate do? Well, it just takes the AND gate, and this is another acceptable way to draw a truth table. I'm sorry, it's getting a little crammed. Video people, this says AND, that says NAND. You'll see me do that. I'm going to address the camera so people are watching it, call stuff out. Okay, so AND we established was this. NAND then is just not that. The not operator of that, inverted. OR gate can become a NOR gate with the output of a bubble. Okay. Now something that I need to call out explicitly, because I have noticed a problem or a challenge with this from lots of students. Not X and not Y is not equal to not X and Y. They're not equal. They're different. So this bar applies to the whole term, whereas the separated bars only apply to that. So the difference is this one, if I draw this in a circuit, is an AND gate where the input is that, right? So the AND of not X, because this is X, right here is not X. This is Y, right here is not Y. And therefore the output is there. This one is that. Hopefully that sticks, because I've had issues with that being a sticking point for a lot of people. All right. When I draw a circuit, I'm going to start referencing things. This is an input or a variable. That is an output. The wire connecting them, you will hear me call a wire or a net. Both terms. Each of these, the NOT gate and the AND gate, the grouping is called a component. So if I'm talking the components of a circuit, it's basically everything that isn't an input or a net. The part that does something. Another way, if I am typing this out, because you can put bars over the letters when you're like in Microsoft Word, but it's obnoxious and time consuming, is instead X bar is the same as writing X apostrophe, or if I'm talking out loud because apostrophe is long, engineers use the term X tick. X bar, X tick. They're equivalent. Just different ways of writing the same thing. Okay, I'm gonna erase all of this. All right. So now we know what these circuits kind of do. Oh, new gate, before I forget. This is what we call an exclusive OR gate, written as XOR. If I add a bubble to the output, it becomes an XNOR, right? Its truth table is nice. It's just saying that if I have A or B, but not A and B. So it's OR, but exclusively ORed. Make sense? Okay. We can start thinking about using circuits as well, writing equations from circuits. And I'm going to draw up a nice big example here. I think this is on page 40 of your book, if you want to follow along. Sorry, make sure I do this right. So you'll see me use these little hoops. That's a way to explicitly point out that they are not connected, right? This wire is jumping over that wire. If I want to explicitly show that they are connected, you can add bubbles to make it more obvious. Okay, so this seems at first like a daunting task maybe to try and write the output function f. But it's not that hard, turns out, right? And the way you do it is like what I showed in the previous one, where you're going to go through from inputs towards the outputs, labeling your nets and what they are. So this is x1 and that's x2. But this net, this whole net becomes not x1, right? Because of this gate. Similarly, x2 flows down here and this is not x2. So for each of these output nets, then it's obvious what they are, right? So x1 and x2. And x2. You don't need to put the multiplier operator explicitly, but helpful to keep track of. Here, another AND gate. We know the terms are x1 and x2. We just have to apply the nots correctly by looking at the input of, oh, it's not x1 and x2. Similarly here, I know I need an x1 and an x2, and it's not x1, not x2. Now I have all of these nets, one final gate. It's an OR gate. How did I connect things with OR? What was the operator look like? Summation. Yeah, plus sign. So F then is equal to x1, x2, or not x1, x2, or not x1, not x2.
So if the AND gates come first, then it's going to be sum of products, and then if you have OR gates first, it's going to be product of sum.
Yes. So that's actually the next vocabulary. This, when you have a series of products connected by OR operators, it's a sum of products. SOP, sum. Right? Because the summing is happening, and the products are the lesser terms. Similarly, I could have a product of sums expression, which they're not equivalent, but we'll call this, I don't know, z is equal to something like that, where a product of sums is this. Now, because of the way that we design circuits from a practical standpoint, the vast majority of our equations are going to end up actually as sum of products. We're going to use this a lot. The product of sums is rarer. We will still do stuff with it, but it's not as common, simply because of the tools that we use to develop circuits aren't as friendly, and it's also much easier to simplify sum of products than product of sums. So if I wanted to simplify the product of sums, I have to distribute. Whereas this is just added. So I will be postponing the homework because the homework has a lot of what we're just about to get to. So we'll talk on Thursday, and where we're going to start really getting into the point of the design. No worry, we still got like 7 minutes left, but we're going to hopefully start building up intuition, and you're going to hear that throughout your program. Probably I did a lot, and all intuition means is your ability to look at something and kind of get a feeling for whether it's right or not. So for me, I look at this circuit and I say there is only 2 inputs. The likelihood that I actually need all 3 terms there is pretty low. intuitively, this circuit is too complicated to achieve the same thing. So like with that Venn diagram where we have those two equal expressions, I suspect that there is an equal expression for F that can be represented with a simpler circuit. Now, why do we care about a simpler circuit? Size and power, right? When we build this for real, and hopefully next time, but maybe next week, I'll get into, I'm drawing these AND gates, but what is that physically? What is that really? Because there are millions of these in your pocket right now if you have a cell phone in there. What is it? We'll get there. But it costs power, it costs area, it costs money to have too many of them. So you as an engineer, part of your job is to not use too many. How do we do that? Well, let's give you a sampling. On Thursday, what I'm going to do is I'm going to walk you through a series of theorems, of rules of how to simplify logic. We don't need them because we can logically think through it. What we can start doing is the multiply and addition work just like an algebra. And we can do things like factoring. Let's factor x1 from this, or the not x1 rather.
Okay. Is redundant, right? Because it's
Exactly.
one or.
Because this is saying or. It's true if either is true. Is it possible for neither of these to be true? It's impossible because x2 is either 0 or 1. So if x2 is 0, not true, then not x2 must be true, right? 0 or 1. The only other option is 1 or 0. Therefore, this is equal to not x1 and 1, but saying a term and 1, well, the and term is always true. So I only care about one column, which means I only care about the x1, right? Simplification, I just simplified it. I then can maybe do something here with this, but probably not. So F ends up equaling x1 and x2, or not x1.
Can't you just get rid of it and one?
Yeah, I don't explicitly need that. If I and 0, it's always false, right? Because I can never get to that 1, 1 in the truth column. Okay. There might be a simplification. Anytime you see something like this where you have a term and then it's not a term next to it, get a little suspicious because sometimes you can simplify that. Don't worry about that for now because we'll get into the theorems because that's not always as easy to see. But I could go ahead and draw the truth table for this expression, right? I only need 2 terms, but my expression is not as simple as an AND gate, but it's a little bit more complicated than that. But now what we've got is F is equal to this, which is equal to that, and I no longer need this whole gate. I don't need that inverter, right? I never invert x2, don't need it. And my OR gate is now only a 2-input OR gate, it gets smaller. And I'd have to rewrite this a little bit to make sure that it is right. But you can see how we're simplifying the circuit, and it saves money in the real world. And for you guys, when you get to the labs and you start building these circuits by hand, which you will do, you have less chances to make a mistake, right? We like simplified circuits. They're nice for you. All right, that's all the content I'll cover. We'll jump into Boolean algebra theorems next week. The homework that's posted, I don't think you're going to do a lot of it until I get through that lecture. You can go look at it and you can get ahead because I don't think it's hard, and it's only like 10 problems. I'm gonna add a couple more that just talk about the gates, just kind of cement that. But anyways, thanks for your guys' attention, and have a nice day.